So the very first thing that we can write down is the definition of transconductance GM. The transconductance of GM of JFET or for any device is defined as the ratio of output current to input voltage. Here output current is in the form of drain current ID and input voltage is on gate, which is VG. So GM can be defined as ID upon VG. In simple words, I will say that VG is equal to GM times ID. Now VG can also be defined as, because you can see VG is the voltage across resistance R, I can define VG using potential division rule. Please note that the gate branch of JFET never carries any current. So this horizontal branch current IG is equal to 0, where IG is the gate current. And hence capacitor and resistance effectively are in series. So I can apply potential division rule. The impedance offered by capacitance C, the capacitor C will offer impedance of minus jXC, where XC will be 1 upon omega into C, where omega will be the frequency at which the circuit is operating. Now to apply potential division rule, I will need the total voltage across the endpoints across which C and R are connected, and these endpoints are nothing but, you can see, points A and B. So the total voltage across the series combination of R and C is nothing but VAB, because these two nodes are exactly same as the output terminals that we have defined. So using potential division rule, VG comes out to be R upon R minus JXC into VAB, but we are calling VAB simply as V. So this becomes R upon R minus JXC into V. You can see VAB, I have simply called it as V, the voltage between the two terminals A and B. So that becomes my VG in the form of voltage V. Next step will be to use the two expressions that we have got. You can see VG was GMID, but VG is also this expression. So GMID and the another expression of VG can be simply compared. So GMID is equal to R upon R minus JXC into V. What I'll do is I will take the ratio V by ID from this. So ID goes here, it becomes V by ID. I'll keep GM as it is. R goes in the numerator, minus JXC divided by R. This can further be written as GM outside. I'll split the numerator into two parts, R and minus JXC. R upon R will give me 1 minus JXC by R. Now you get a complex term here, but this complex term 1 minus JXC by R will have a very small real part compared to the imaginary part, because we have made an assumption that XC is much greater than R. This can be approximately written as minus JXC by R. This is mainly because XC is very much large compared to R. Because XC is very large compared to R, XC by R is very large compared to 1. So even though it's a complex quantity, the imaginary part will dominate and hence can be simply written as minus JXC by R. So with that, we come to the last step of the derivation. We finally define the expression for Z. Z was nothing but, we had written Z as V upon ID. We already have got V upon ID as GM into 1 minus JXC by R. But you can see we have just now replaced 1 minus JXC by R with only minus JXC by R. So this is almost exactly same as, I'll keep minus J outside, it becomes GM XC by R. This means VG from this equation becomes ID upon GM.